Hello, my name is Sab Matsumoto, and I am a mathematics professor at College of the Canyons in Santa Clarita, California. Today, I am going to give this presentation entitled Mathematics and the Pandemic, and we'll be talking about 4 topics. What are they? Well, you will see as I share my screen. Okay, so let's get started on this. Here is the outline of the topics today. First, I will be talking about the exponential growth model, which is very appropriate for a topic like the pandemic. And then we'll be talking about logical fallacies, namely 2, false cause fallacy and the correlation-causation fallacy. And then we'll explain what the vaccine efficacy rate is. This is a really big topic in the news and current events, but many people actually do not know exactly what that efficacy rate means and implies. And then I will finish with Calabresi's Fable, which has to do with risk and irrational fears. And then I'll have a couple of book recommendations before I take your questions. So I hope you will stick to the end. All right, so let me, by way of introduction, let me go back and look at what's been happening in the world in recent days. All right, so back in the spring of 2020, if you remember, and I remember this very clearly because Saturday, the March 14th, 2020 was a Saturday. It was a Pi Day, 3.14, and I was at a pizza place, which happens to be doing a little competition or a race to see how many digits of pi their customers can say or write down. Right, and they had somebody who had 5 decimal places of pi accurately, and I guess whoever wins will get $100 gift certificate at that pizza place. So I was excited, and of course I wrote down the first 30 digits of pi, and I believe I had won because I mean, I can't imagine that they found somebody who can write more than 30 digits of pi. But then the shutdown followed. After that day, basically, the economy shut down, most businesses closed, and I have never heard back from that restaurant again. So my guess is that maybe that pizza joint closed. Never got my $100 gift card. But then, of course, you remember, and then summer came, and millions and millions of infection cases were disclosed, and many people actually, unfortunately, passed away. Fall came. Operation Warp Speed was announced in order to develop a vaccine. And then remote instruction became a sort of a norm as you continued to get your education. And then finally in winter, vaccines were approved. The first one was Pfizer. And then today we'll be looking at data published by Pfizer in their clinical trial. And then this is something personal, but in spring of 2021, I actually took a sabbatical leave to work on an OER project. And OER is, of course, Open Educational Resources. And I came out with the OER called Liberal Arts Mathematics 2nd edition, which is downloadable at the math department home page. And let me just show you this. Because you have decided to watch this or attend this presentation today, just for that and to express my appreciation, I am giving a free copy of my liberal arts math book to all of you. In fact, it is free to download for anybody, but it's right here. If you go to the department website for the math department at College of the Canyons, you can download this, the 500 plus pages of liberal arts mathematics. I didn't write all of it. Many of these pages were written by others, and I added probably hundreds of pages as well. All right, so the reason I'm mentioning this book is because today's topics mostly come from this book. All right, so exponential growth is in chapter 6. And by the way, at the end of every chapter, I have a section called 4 Further Explorations, FFE sections. And so the exponential growth and COVID-19 is actually in that section for chapter 6. Logical fallacies are in the first section of the book. Correlation and causation are in that statistical chapter in section, chapter 5. And Calabresi's Fable is found in chapter 4. Now, I know that most students in science and math would not take that liberal arts class, but this is a great and maybe one of the rare opportunities for you to see what liberal arts math is like. It is really practical applications of mathematics, and you should actually look into it. We talk about many great and practical topics. All right, so let's go to topic number 1, exponential growth. All right, now I am going to give you a scenario which seems to have nothing to do with COVID-19, but hang on with me here. Okay, so imagine that on March 15th, March 1st, I'm going to use a pen here. Initially, you have $30 to invest in cryptocurrency. All right, and then you see that the value of this cryptocurrency grows every single day. Wow, this is really good. And then 14 days later, on March 15th, you discovered that your $30 of investment has now grown to $3,487. Not a bad investment. All right, let's calculate the growth coefficient with the base E. Right, and E, of course, this is the exponential function, and find the daily growth rate. All right, how much is it worth if you continue to hang on to this? You have March 15th. So if you wait for another month or so, and how much would it be worth on March 18th if you continue to, or if the cryptocurrency continues to grow at the same rate? Okay, that's a question that I want you to think about. So because this is assumed to be exponential, we have a formula here. Now, if you are a liberal arts student, you may not be able to get this, but that's okay. Just listen, and then it'll make sense. Okay, this is called the exponential function or exponential growth model. P naught being the initial value. All right, and so the let's do some math here. Okay, this is not a difficult level of mathematics. P of t is equal to P naught times k e to the kt, right? And so because of the initial value, you know that pt is 30. You had $30 e to the kt, right? And the second equation here will give you P of 14 is, of course, 30 times e to the, of course, t is 14, so this is 14k is equal to 3,487, right? And so that means e to the 14k is the fraction, the coefficient, quotient of 3,487 by 30. All right, and so now comes the cool part. You take the the logarithm, the natural logarithm of both sides, and you get the natural log of that fraction is 14k, right? So you can easily find this k, the coefficient of the exponential growth. It's 1/14 times that natural log. Okay, you can go ahead and use your calculator. You need a scientific calculator to calculate this or to evaluate this, but k turns out to be approximately 0.3397. Okay, and in fact, the number is right here. Okay, and so it's relatively easy to find this number, right? If you're a pre-calculus or a calculus student. Now, there is no reason to have to use e as the basis, right? And in fact, if any any exponential function can be written with pretty much any positive base. And so if instead of using e, we can use e to the k as your base, and that would actually reveal something very important, because if you use e to the k, this is the value of k, that turns out to be 1.4045. Okay, why is that so revealing? Why is that so significant? Well, because this tells you that your money is actually increasing at 40%, right? 40.45% per day. That is your rate of return every single day. Wow, that is really good if you are investing your money or cryptocurrency. All right. If, however, this is the number of daily infections, that is another problem. Okay. Now, so this sort of underscores the importance of abstraction. Okay. And what I mean by that is mathematics is powerful, It's a powerful tool because of the power of abstraction. And so what I'm trying to say here is that this exponential growth, which we just used to calculate, to carry on financial calculations, actually applies directly to the number of COVID infections. All right. So what we found, and this is based on the CDC numbers, back on March 1st, which we set this equal to t is equal to 0. We considered March 1st to be the initial date. There are 30 cases in the entire United States. All right. But within 2 weeks, when t was 14, this is 14 days later, okay, the number of cases turns out to be, new cases turns out to be 3,487. Now, these are the numbers you just saw, right? And so the exactly same operations, exact same exponential model can be applied with the same coefficient k. And what we found is, well, by the way, I didn't do this for you, but if you plug in t is equal to 48, that's 48 days later, which happens to be April 18th because March has 31 days. If you plug in that number here, you will get $361 million if this was a value of cryptocurrency. If this is a number of new patients infected with COVID-19, then this means that on April 18th, you will have 361 million new cases in the country. And by the way, this number is bigger than the entire population of the United States. Okay, now, why is it so much smaller? This is the real data published by the CDC. On that day, April 18th, theoretically, we should have had, if exponential growth were to continue, we would have had over 360 million cases, but we only had 720,000. Now, that's still a big number. Okay, but the reason is because something was done right around this time to stop or to decelerate, to slow down, to inhibit the rate of infection. All right, and so you can see that the measure resulted in the much fewer number of cases compared to the exponential growth. See that this number here is with the assumption that nothing is inhibiting or slowing down the process of the exponential growth. All right. So here's a question that you may want to ask yourself. If you are in charge of public health, and if you see these two numbers here, and you know about your exponential growth, in other words, you know the model that we talked about here, if you have this knowledge, and if you are trying to slow down and stop the infection, the spread of the disease, what would you do? Okay, I think you would be forced to take the drastic action because these two numbers, 14 days apart, means, and again, this tells you that it's a 40% a day growth. And with that, you would expect that by the way, this is April 18th of 2020, not 2021. Okay, only in a matter of days, you would have the entire country infected with this disease. Okay, that's what the math was showing. And that is why such a model is important to understand. Okay, so that is our first topic. Now let's move into the second topic, which is logical fallacies. All right, now we have many types of fallacies. And by the way, the reason this is a part of mathematical studies is because logic is at the foundation of mathematics. And in fact, study of logics is sometimes called meta-mathematics, right? There are many types of logics, fallacies, and I'm just going to focus on these two, false cause, sometimes called post hoc in Latin, and then correlation-causation. So what are those? First one, post hoc is false cause, right? This says because X happened, and then Y happened, X must have caused Y. Okay. Now you can, clearly see that this is a faulty argument, right? So let's say somebody said, or let's say I said, last night I wore my blue and white wig, and by the way, this is me here watching a Dodger game, and so I wore that wig as I always do to cheer up the team, and the Dodgers won. So I'm going to wear that every single day to watch the game. Okay, you can clearly see that this is not a good argument, right? How about this one? Driving. Okay, the average driving speed on highways sharply increased in 2020. By the way, do you experience this? I do. Every time I drive on highways, freeways around LA, people are driving much faster in 2020 and 2021. And so when the numbers, the average driving speed increased, the number of traffic-related deaths in 2020 sharply dropped. And so driving faster saves lives, okay? Because this happened, and it's followed by a lower death rate. That means driving faster saves lives, correct? Let's keep driving fast. No, the problem here is, of course, there's a common underlying cause. And the common underlying cause that resulted in this phenomenon of faster speed and the lower death rate, the number of deaths, is that there were not as many cars in 2020 because of the shutdown, okay? The fewer the cars are on the road, people are driving faster, and there were fewer deaths, all right? So it's not that X is the cause of Y, it's just Z caused both X and Y, Z being fewer cars overall. Okay, so here is an example that I saw this is back in January 22nd. The Defender is an online medical journal, and the headline says, "Home Run King Hank Aaron dies of undisclosed cause 18 days after receiving Moderna vaccine." So if you look at this headline, you can clearly see, right, the author is not clearly saying that these two things are linked. But the hint is there, right? The implication is that this vaccination has something to do with the death of this super athlete or former super athlete. Hank Aaron, by the way, is the, for those of you who don't know, the former Major League Baseball player who broke the home run record of Babe Ruth back in the 70s. If you were to go into my office, and if you are to just look at the side of my window, you will see a baseball, okay, signed by Hank Aaron. I have an autographed a ball. Now, don't go in there try to steal it, but because I'm not going to let you, okay? But he actually died at age 83. At age 83 of a natural cause, passed away peacefully. All right, but the intention of this headline is very clear. All right, and so they are trying to let the reader to sort of connect or associate the vaccination with the death. And so this is one of those examples of a post hoc fallacy, right? And you have to be aware of these things. You know, be careful when you read things on the internet or in paper or in other places. The second is the second form of fallacy I want to talk about is correlation causation. All right, there is a correlation between X and Y, and therefore X is the cause of Y. Now, this is very, very prevalent, very widespread, and you have to be really paying attention. Practice your critical thinking skill to make sure that you don't fall for this. Right? When ice cream sales are high, more people drown. Okay, there is a clear association. This is called a positive correlation between the ice cream sales and the number of people who drown. And therefore, ice cream must be causing people to drown. No, okay? And again, you can see the clear underlying cause, right? Here's X, here's Y. Z, the underlying cause is, yeah, hot days, high temperatures would result in higher ice cream sales. And because more people are swimming, that would cause more people to drown. All right, so it's not that one is the cause of the other one. And so here is that fallacy applied in case of COVID-19. Now, watch really carefully. Okay, what does this graph tell you? The average number of new daily infections. Okay, for those people who don't wear masks, it is much higher than those people who wear masks 80% of the time. Right, and then 40% of the time, if those people wear masks 40% of the time, it's sort of in the middle. You can clearly see the correlation, right? Okay, so let me ask you this question, and you have to be very careful here. Does this graph prove that wearing a mask is going to slow down or reduce the risk of infection? Okay, certainly you see a correlation. Causation, that is actually questionable, right? We don't really know definitively if the mask is the cause of less infection. Now you may be surprised at this, right? Now, if a statistician is writing a report, they will never say that the masks are the cause of the fewer infections. They will say these things are related to each other or associated with each other, but you cannot establish causation based on this graph alone. Okay, now there may be other evidence. I am not saying it doesn't, right? But this graph or this data alone cannot prove causation. And you have to be careful, because if you claim that, you see this graph here, this means that the masks are going to protect you, right? Now, this may be true, but you really don't have enough evidence to establish causation. And people will see the faulty argument in what you say, all right? Okay, let's move on to the third topic, which is the efficacy rate of the vaccine developed by Pfizer. All right, so these are the data, and these are very, very important numbers. These are the raw data published by Pfizer after their 2020 clinical trial. This is the first major clinical trial, well, I mean the third, but the very important clinical trial that was used to get the emergency approval by the FDA. So what does it mean? Well, let's take a look. Right. First of all, a placebo is a sugar pill that looks very much like the real pill or the real vaccine, and it's often, well, it does not have any active ingredient. The real vaccine, and so what they did is that this is a large size trial that you can see. About 18,000 people were given the real vaccine by Pfizer. Okay, about the same number of people were given the fake vaccine, which is just maybe a saline water or something that some shot that did not have any active ingredient. Okay, and this group is called the control group. The ones who actually got the vaccine belong to what is called the treatment group. All right, so about the same number of people were given this. And I mean, given the vaccine and then placebo, okay. And so this is a double-blind, comparative. These people are randomly chosen to be in these groups. And so now what we do is we look at the number of people who are infected. That's 8 in the vaccination group and 162 in the placebo group. Right. And then you divide this number by this number, and that's the positivity percentage. 0.044% of those who were vaccinated with this Pfizer vaccine during the trial developed COVID-19 or got infected. On the other hand, in the placebo group, about the same number of people were given the placebo, and 162 of them got infected. That's 0.884%. Notice here, both are less than 1%. Okay, this is back in December of 2020 or in the fall of 2020. But even then, less than 1% of the people were still getting sick. Now, does that mean that COVID is not significant? No, I mean 1% is a big number when you talk about 330 million Americans, right? Or 8 billion people in the world. Okay, so now how do you calculate this efficacy rate? I'm going to tell you how to calculate it, and I want you to look carefully and see what it implies, what it tells you, right? So first we have that control group positivity rate, 0.884%. Okay, that is the percentage of the people in the placebo group, control group, who got infected, compared to the treatment group, where the positivity rate was 0.044%. Okay, and that is the percentage of the vaccinated people who developed COVID-19 infection. The vaccine efficacy rate is found as follows. You divide that treatment group positivity rate by the control group positivity rate. See, the control group basically is the general public without any vaccine. I mean, they were given a placebo, but it's really nothing, right? So in absence of, in this case, the Pfizer vaccine, you would expect 0.884% of the population to be sick. That's the denominator. But given the vaccine, that the percentage goes down to 0.044%. So you take T and divide it by C. Okay, now this is the rate of the people who would get COVID-19 if nothing is done. And then you subtract it from 1. And so when you do that, you get 95.03%. Okay, and that is considered, or that is defined as the efficacy rate. All right, now let's see how you can interpret this. It is a good exercise in critical thinking. What does this number mean now that you know how they found it? All right, this is what it means. Imagine a random group of 100,000 people. Okay, so you have, imagine the whole world, not the whole world, maybe a county or a city with 100,000 people. Okay, and out of these 100,000 people, 884 of them would be infected if there's no vaccine. Okay, but only 44 of them would be, so 884 people will get sick without the vaccine. But if they're vaccinated, that number goes down to 44. Okay, so that's what those numbers mean. And so 95% of 884 people, now these are the people who would get, COVID-19 because they were not vaccinated. Out of these, 95% of them would be prevented from getting infected. Okay, that's what that 95% efficacy rate means. All right, again, what that means is that 95% of those who would have been infected with COVID-19 had they not, if they don't get vaccinated, 95% of them would be prevented from getting infected if they were to be vaccinated. All right, so that number, okay, maybe I can say this is, so basically 884 and then 44. And it comes down to, again, it's 95%, right? So if you have 100 people who get vaccinated, let's just assume it's 95. It's a fraction, but it's 95%. If it's 100 people who would get, if 100 people, unvaccinated 100 people would get infection, right? This means only 5 people, vaccinated people, would get infection. So in other words, 20 to 1, that's the ratio of unvaccinated people to the vaccinated people among those who get infected. All right, so I hope this makes sense. What does it mean then? Let me just ask you a couple of questions, true, false questions. Does it mean that about 5% of vaccinated people will get COVID-19? Okay, and some people actually believe that, but no, that's not what it means. Nor does it mean that 95% of unvaccinated people will eventually get COVID-19, right? No, it doesn't say that. In fact, in the clinical trial, the data you just saw, even if you're unvaccinated, only less than 1%, 0.8% of the unvaccinated people did get COVID-19, right? So this is, of course, not true, nor is this true, okay? It's actually 0.04%, well, it's much, much smaller. Some vaccinated people get infected. Is that right? Of course they do, all right? Because again, any, no vaccine is 100% effective, right? So there will be, these are called breakthrough cases, right? There will be vaccinated people who get infected. And then some unvaccinated people do not. Of course, that's true too, right? And so these things do happen. Okay, but this does not mean that the vaccination is ineffective. Again, what it means is this, and this is maybe the clearest statement I can give you on the efficacy rate. For every unvaccinated person who gets infected, there are for every vaccinated people who are infected, there are 20 unvaccinated. What did I say? For every vaccinated person who gets infected, there are 20 unvaccinated people who get infected, right? And so that's the ratio, right? And in fact, if you look at the data, you can see this. Now, let me go back to the breakthrough cases before I show you the data. Suppose you have 100 million people who get vaccinated, right? And that's pretty close to the number of people with full vaccination today. So again, 0.044% of 100 million is 44,000 people. Right? This is the positivity rate of infection among the vaccinated people, right? So even with such a small percentage, because the denominator is so big, we could expect about 44,000 people, vaccinated people, to get sick. And now if you focus on that, right, you say, well, look, I mean, thousands of people are still getting sick with COVID after being vaccinated. Is that true? Yeah, it's absolutely true. But what you want to look at is the rate of infection, okay? And this is the number that we should be focusing on, because this number is far, far less than those people who are not vaccinated. Okay, does it mean that vaccination is not effective? Of course, the answer is no, right? And by the way, the efficacy rate against the Delta variant, this is a more recent result, is about 88%, according to the Johns Hopkins University study. And the recent data, and I know this is really small and you can't see it, but the recent data sort of confirms what we have been talking about, right? And so what this shows is that, and on the right-hand side is the share of overall cases among the unvaccinated people. And this is the share, the percentage of people with COVID who are vaccinated, all right? So all of this, both of these are showing people who are infected with COVID-19, who tested positive. Among those who tested positive, this percentage are unvaccinated, and this percentage is vaccinated, right? The difference is very, very clear. The science is, very clear on this. But it depends on how you report it, and you can report the truth, but not tell the whole truth, and that's what you have to be aware of. Okay, so the breakthrough cases are here. You can see that among the vaccinated, the numbers are much smaller than the well. Okay, so let me just go ahead and say this. So the number of infection cases, okay, among the vaccinated, and this is in the entire country from January of this year to the July 22nd. There have been 21 cases called breakthrough cases, 21,000 breakthrough cases among the vaccinated. But in percentage terms, it's 1.35% of the vaccinated people. If you go to hospitalization, it's 0.79%. For death, it's 0.244% of the vaccinated people. So breakthrough cases, hospitalizations, and death do occur, okay? But the percentages are much, much smaller. Now, we hear about side effects as well, serious side effects, okay? And what happened in that clinical trial by Pfizer is that 2 people who received vaccines actually died during the trial. Now, you can report that and say, look, 2 people died who are vaccinated with this new vaccine, died during the trial. What more do you need to say that this vaccination is bad for you? Well, it turns out 4 people receiving the placebo also died during the trial. And by the way, these 2 people died of causes not related to COVID-19. So again, you have to pay attention to the people who are presenting data to see what the real, situation really is. Okay, none of these people, by the way, died of COVID-related causes. And when they looked at what is called serious adverse events, and there's a well-defined, there's a definition for this, medical definition for these events, 0.6% of the treatment group did suffer serious adverse events, and then 0.5% of the placebo group also suffered similar adverse events. And so this is called a statistically insignificant difference, right? And the source is the New York Journal of Medicine. You may have heard of this medicine. This is probably the #1 medical journal in the world. All right, let's go to number 4. All right, so what does this mean? Calabresi's fable and irrational fears. Well, so Calabresi, Guido Calabresi, is an Italian-born American judge. He's a federal judge. Even to this day, he is a judge at age 88. And what does he do? Well, he's a former dean and professor of the Yale Law School. And he came up with this story called the Fable, his fable, What is his fable? Now, if you may have heard about this, if you have, don't say it. But he says, well, look, somebody came up with this innovative, exciting, life-changing new product, all right, which is going to save you tons of money. And it's going to save you tons of time. It's going to allow you to save quality time with your family and friends. And it's going to take you to many places you've never been before. A whole new world is going to be opened up to you because it's going to allow you to go to places that you could never go otherwise. And it gives you so much convenience and comfort that everybody would want to have this. The only problem is that about 40,000 Americans will die if all the people in America decide to get this. And it's not very cheap. It's about 20,000 to 100,000. Average one is about $30,000. Okay, now who would buy this product? It's going to kill 40,000 Americans every single year. You may have already figured this out, but the product he's talking about is the automobile, the cars, right? About 30,000 to 50,000 people die in car-related fatalities every year in America. Many more are injured. Okay, so should we ban the use of cars? I mean, you want to save lives, right? There's nothing more precious than human lives. And so why are we continuing the use of cars when so many people die? Okay, human life is too precious to sacrifice for a little convenience, right? What do you think? Well, so this is called irrational fear, and there have been many books written about this topic of irrational fear and risk-taking and so on. This whole idea is to be afraid of low-risk things while being unaware of much higher risk factors. Okay, so between January 1st and July 22nd, in the state of California, 93 vaccinated people died of COVID-19. 93 vaccinated people, okay? But on the other hand, over 38,000 unvaccinated people died of COVID-19. So what this is saying is, if you look at COVID-19 related deaths, 99.756% of them were among the unvaccinated. Now, you look at this number and say, wow, 93% of the people died within like 6 months, right, after they get vaccination. And so then you may get scared of getting the vaccine. And this is what I mean by irrational fear, because I mean, what's the alternative, right? Because a lot more people who are unvaccinated ended up dying with the same disease. Here's another one, and you may have heard this in the news, Johnson & Johnson vaccine. After 7 million shots were given worldwide, 6 women had blood clots. Okay, and so they suspended the use of this particular vaccine for a while. Is that an irrational fear? Okay, well, you decide. I tend to think that's true, but again, this is something that the science just tells you. Statistics and science can tell you the figure. And what you do with that is really a question of human behavior, psychology, and policy and politics. Okay, we'll talk about this in a moment more. 299 people died of commercial plane crashes in 2020. 200, it's 300 people. That's terrible, right? I mean, you see the picture of a plane crash and that's horrible. So should we just stop flying? Well, again, irrational fear may say yes, but the world goes on and most people in the world decide to travel by air, even when you see these things. So there are some, in the same idea, same context, there are some wrong questions asked or talked about in the pandemic, right? So for instance, there was a reporter who said this: can we guarantee that our children will not be infected or die with COVID-19 if we reopen our schools? Okay. Now, what's the honest answer? If you're a politician, you probably will not say that, but the honest answer is no, of course you can't. Nobody can, right? In fact, nobody can guarantee anything, right? Even if there was no disease, when we open our schools, people and children may die of a school bus related accident, right? Or they may die of some other causes. So we can't guarantee that. So this is not even a fair question, okay? What we do is we minimize the risk, and that is really what the question should be about. How about this one here? Should we not require weekly negative test results? in addition to vaccination, in some workplaces, in addition to the vaccination, you also have to have negative test results. Okay, if you're traveling to places like Hawaii, it's not good enough to get vaccination. They will also want you to have a negative test result, right? To guarantee 100% safety. Well, you see that the problem here is that even the negative test results within the last 72 hours will not guarantee 100% safety, right? Because you could have gotten infected within the last 72 hours after the test was given. So if we talk about 100% accuracy or safety, that may actually live in a mathematical world. Like I am 100% certain that the sum of the internal angles of a triangle is 180 degrees if you assume Euclidean geometry. That's 100% certainty. Okay, but in the real world, especially in the real world of pandemics, you can't really talk about 100% safety. And again, this goes back to that irrational fear. What are you afraid of? Where do you draw lines? So points from that fable is are these. No protocols or policies are perfect, right? And science and statistics can calculate risks. And that's what the clinical trials do. Where do you draw the line? That is a real question. In that case, the efficacy rate was 95%, all right? And it is a quite high of as an efficacy rate, 95% is extremely high. And so that is a pretty clear winner in terms of the new vaccine being developed, because most flu vaccines are nowhere near that effective. The flu vaccines, okay? So the questions are like, how much are we willing to tolerate? Okay, because I mean, after all, we drive cars and we fly in airplanes, even though it's 100% safety is not guaranteed. How many lives are we willing to, just sort of sacrifice? In the case of cars, 30 to 40 to 50,000 people a year die because we use cars, but we still tolerate and we use cars almost on a daily basis. So this part is not a scientific question. It's a question of policy, sociology, and psychology. All right. Another example is a driver's license. Okay, so in most places, you cannot drive cars unless you are 16 or older. So what happens on your 16th birthday? All right, the teenagers just all of a sudden become responsible and mature on their 16th birthday? No, okay, but based on statistics and data and so on, the society has drawn the line at age 16 as a minimum age for driving cars. Okay, so same kind of thing has to be done. I mean, these policymakers do have to draw the line, and that is not a question of science or statistics. It's really a question of policy, and it's a political question. All right, so this picture is from the Los Angeles Times, September 29th. And people are, of course, protesting. Take a look at this. This is what I want you to focus on. If masks work, then why do we need to get a vaccination? Is that a good question? Think about the logic of this and compare that with something else, maybe. All right. The question is, if masks work, why do we need to get the vaccination? Right. Let's make this abstract. This is what we do in mathematics. Right. If X works, why require Y also in addition to X? Well, a possible explanation could be X could reduce the risk and Y could also reduce the risk independently. Neither of them is 100% effective. So why not use both, right? In order to minimize the risk. So this would make perfect sense. So in other words, what I'm saying is there is nothing inherently wrong about requiring two things. Now compare this to something like this and see how ridiculous it sounds. If seatbelts save lives in cars, why do we have the speed limit? Okay. Well, the thing is, this saves lives, and so does this. And so it is possible to have both and make things safer, right? So there are all kinds of things, logical questions, exponential model questions and other questions that you can ask from mathematical standpoints in dealing with a pandemic like the one that we are facing. All right, I'm going to conclude this presentation with some of the recommendations. The data detective, if you're interested in pursuing the correct and maybe incorrect interpretations, information, misinformations involving data, this is a really, really good book. This was published very recently, I think last year, by a British author, Tim Hartford, and it has many great stories about how people were misled, misinformed, came to wrong conclusions, okay, partly based on data, but really based on our humanity. Our brain is just not perfect. Okay. Innumeracy is a much older book, probably 30 or 40 years ago, in a similar spirit. But I highly recommend the Data Detective if you really are interested in finding the truth in our data-driven world. And then the more recent, another recent book is Artificial Unintelligence. And you can see from the title what this book is about. And finally, this is a slightly different type of book, but it's a book that I read and I really, really enjoyed. This is probably one of the best books I've read during my sabbatical, Mathematics for Human Flourishing. And this is written by a professor at Harvey Mudd College here in Southern California. Wonderful book about what mathematics is and what it does for the human spirit. So I highly recommend that. Okay, I will take questions at this time. Please let me know what you have questions about.